Welcome to Plutus STEM, and today we are covering the CFT diagram for octahedral complex. So, today what's in the lecture? In the lecture today we will discuss how the CFT diagram is drawn and why particularly that specific arrangement has been drawn. What is its significance and how ligands affect the splitting pattern of the orbitals and gives rise to a particular splitting pattern that is related to the specific geometry for the complex. So, let's get started. So let's first assume that an octahedral complex is placed inside a cube. So an octahedral complex looks like this, where four of the ligands are placed in the plane, while two of the ligands are lying above and below the plane. Now, putting in the same geometry, you can see if I require four of the ligands in the plane, I have four different types of d orbitals. This corresponds to the dxy, dyz and dzx type of orbitals. While the only orbital that I have on the axis is the dx square, y square, and another orbital that I have is the dz square lying on the z axis. So if I see only the orbitals that I require should have this and this geometry, and when these two completely combine, that means if this is the metal center, four of the ligands will be touching four of the faces of the cube. So that means the ligand will be approaching from those directions where the orbitals are aligned in that particular direction so that a particular geometry can be achieved. Now, just looking at this, now I require formation of the ligand. Now I require the bonds which are above and below the plane. So for this, the orbital I require should also be of the vertical geometry, which is dz square. Now here two ligands will approach from this direction and two will approach from this direction. Now, since CFT considers that the bonding between the metal and the ligand is 100% ionic, that means the entire process will be governed by the electronic repulsions that is been happening between the ligand and the metal. Now, metal do possess some unpaired electron density, and ligands are carrying also negative charge density. So when the ligands in the ligand sorry when the ligands empty orbit filled orbitals are approaching the metals filled d orbitals, there is electronic repulsion between them, and what happens is the d orbitals energy due to the electronic repulsion starts to rise. Now, moments before the ligand is completely approaching the d orbitals for the formation of bond, the d orbital, because of such large repulsion, they split. Now, since the orbitals, which are the dx square y square and the dz square orbitals, are the directions where the ligands were approaching, they suffer the maximum amount of repulsion and hence they will be raised to a higher energy compared to them. The orbitals we have. Similarly, now the orbitals which are left are the dxy, yz, which are not on the axis. Hence, they suffer lesser repulsion, and compared to those orbitals, they will be much more stabilized. Now, now we have seen that these two orbitals have split into two sets of orbitals. The above set of orbitals is called as the EG set of orbitals, where G refers to Gerard. Gerard means that it is symmetrical, and that we can look that the octahedral complexes are symmetrical in nature. So, and the lower set of orbitals is called as the T2 G set of orbitals. This is our energy that is increasing from this in this direction. This is our d orbitals in ground state, while these are the orbitals which are in excited state. Now, if you need to find the energy of these orbitals, you need to know the energy of the ground state, then of the excited state. Only then you can find the energies of these excited state. Now, to save up the trouble, we are assuming that the average energy along the excited d orbitals is zero, and this point of average energy where we are absorbing equals to zero is called as the barycenter. Barycenter, where the average energy we are assuming to be zero. Now, along this energy center, now we'll need to know how much they are being stabilized. This entire difference of total energy is called as crystal field splitting, and based on the geometry, it can have, for O refers to octahedral, T refers to tetrahedral, and when you are dealing with square pinna, it will be del SP. So now we have total of 5 orbitals and 2 orbitals are raised to high energy. Now, since they are raised to higher energy, they are suffering more repulsion. The total contribution of repulsion that they have will also be 3 by times of the original ones. So, here, this difference of energy is represented by, since it is plus, can be represented as 0.6 del O. While for the lower one, it will be 2 by 5 times of del O, which is negative times because it is lower than the average energy level, minus 4 del O. Now, in your exams or some books, you can also find that 0.6 del O sometimes be also written as 6 dq. And dq is what? Is the energy conversion unit in which 1 dq equals to 10 times of del O, whatever you are having. So 0.6 mil equals to 10 multiplied del O and you will get 10 dq. So this is the conversion unit. Okay, so this is the reason why we get a specific splitting pattern based on the orientation and the approach of the ligands and the orbitals that are being utilized. I hope this would have cleared your doubts regarding how to make the CFT diagram of octahedral complex and why a particular splitting pattern is observed. In next class, we'll move towards square planar and then we'll tetrahedral, and we'll cover more such topics in the future. So please like and share and subscribe. Thank you for joining us.